This is the end. Hold your breath and count to 10.
5.3 is on the normal distribution, and we'll do this in 2 days. So, first of all, let's talk about what a normal curve is. This is very important. This is one of the most important things in statistics, I would say. And it's really important in science as well. What a normal curve is, it's a curve that's a bell curve. So it's like this curve right here. To get what I mean by why it's a bell curve, because, for example, you could put like a bell here, ding-a-ling-a-ling, right? That's what it's supposed to be looking like. So that's a bell curve. And it's symmetric about the mean. Okay, so the mean is going to be right in the middle. Remember that the mean is what we mean when we say average. So it's kind of like the average amount. This is the mean right here. And like the reason it goes up there is because underneath here it shows how many people, for example, if we're talking about people, how many people are at the mean. So I think maybe an example, I should give you an example here. Say that you wrote a test, a huge number of students, all the grade 10 students in BC write the provincial exam for math, and then they record all the marks. Well, most of the kids are going to be right around the mean. In fact, probably the most of all are going to be right at the mean. And you'll have, a smaller amount which are a little bit higher than the mean, and a smaller amount still that are way higher than the mean, and a very, very few that are getting like 100% way up here, right? Same at the below. You're going to have a few people, or quite a lot of people, who are just below the mean, like a little bit below. And then down here, you don't have as many people who are a long way below the mean. And down here, you got your people who got 0, 1, 2. There's not a lot of those people. Thank goodness. Okay, and it's symmetric about the mean, right? If you look on the left-hand side of this thing, it looks exactly the same as that. It's like a mirror image. Okay, something else about the normal curve. 50% of the data is above the mean, and 50% of the data is below the mean. So these people right here, remember, are all the people who have the mean value. Half the people are above that, and half the people are below that. Next. Mean, median, and mode are all the same value. So if the mean is at this spot, then the mode is also at that spot. It's the most common, yeah, we can see that from the drawing. And it's also the median value. It's the middle value. And that kind of makes sense if half's below and half's above. The probability, normal curve, the probability that an event happens is equal to the area under the curve. So let's say, for example, you wanted to know how many people got between exactly the mean and up to this point here. So you wanted to know how many people got in this range right here. Well, the way you'd figure that out is you could figure out what's the area of this red shaded area here, and whatever that area is, that's the probability of someone landing in that test score right there. Okay. Next. The entire enclosed area is 1. So if we were to find all the area below here, the whole thing, the area would be 1, and that makes sense because the probability of someone being somewhere below here is 1. It's 100%. They have to fall somewhere below there, right? They have to have a score if they wrote the test. Next. Real data often, so this is important, the real data can often be approximated by a normal curve, but it's probably not going to be exactly a normal curve. There's lots of places in life where we get curves that look a lot like this, but it's very rare that they're exactly this, where the mean, the mode, the meaning are exactly the same at the same spot, and 50% of the data is above and 50 is below, blah, blah, blah. But there's lots of times that'll be close to that. So I already gave you one example with test scores. Another is people's heights. A lot of people are about a certain height, I don't know what, maybe like 5'8" or 9" or something like that, and then you get people who are taller and taller and taller. You probably have your 6 feet people up around here somewhere, and if you keep going, your 6'4" and your 6'5", and probably out here you have your 7'1" or whatever. They're really, tall people. Same going down this way. You have your 5 feet people, your 4 foot something people are way down here. So it's a normal distribution, not perfectly, but close. Error in measurement. When we measure things, some people are right on, some people are a little bit off, some people are way off, but not as many, etc. Blood pressure and test marks are some more examples. So this is a normal distribution. It's very, very important. So the first thing we're going to do is we're going to sketch the following normally distributed samples. So let's focus just on this bit because we kind of have two questions here. This is the first bit. So we're looking at the weight of luggage, and we have mu, which remember is the mean, and we have sigma, which is the standard deviation. So there's men and women, and the men and the women have the same mean. Okay, so the way we're going to draw this is we're just going to draw a line here, and we're going to put the mean right there, 6.35. That's the mean. And they both have the same mean. And remember, it's going to be symmetrical around the mean. So far, it looks like they're going to be the same. But they're not going to be exactly the same because the men have a bigger standard deviation than the women do. What does that mean? It means the spread of data is more for the men than it is for the women. So let's draw the men first. It's going to be pretty wide because they have a fairly significant standard deviation. And it's supposed to be symmetrical, which I'm probably going to fail at. And it's not bad. I'll go with that, right? The biggest amount of men are at the mean, and then it gets lower and lower as you go higher, and it gets lower and lower as you go lower. Okay, let's draw the women now. So for the women, they don't have the same standard deviation. So you might think that what you're going to draw is, well, I just won't go as wide, and I'll go something like this. But that's not actually the way I want you to draw it. Why not? Because I want you to assume here that we have the same number of men as we do women. So if this is all the men under here, if we were to draw this like that, would we have the same number of women under here? No, there's a smaller area under there. We need to have the same area. So how are we going to do that? We're going to have to draw it going higher. So I haven't really left myself the appropriate amount of space, but it's going to have to go up higher like this, so that we, ideally, if I'd drawn it perfectly, and this isn't bad, the area under the green one should be about the same as the area under the red one. Okay, they both have the same mean, they're both centered at 6.35, but the men's is wider because they have a greater standard deviation. Okay, let's look at the second one over here. Okay, this time the means are different. One's at 5.8 and one's at 3.9. So let's draw both of those first. 5.8, 3.9. You don't have to be accurate about where you put them or anything. So they have the same standard deviation. So what does that mean about the curves? They should look exactly the same. If I draw the men's like this, not great, but you get the idea. Then the women should look exactly the same, but it should be centered at this one. So this is very hard to make it look the same. It's a little smaller, but anyway, you get the idea, I hope, that they have the same curves because they have the same standard deviation, but they have a different mean because they're centered at different numbers. Okay, all right, now this, wow, we got a lot to fill in here. So this is a normal distribution curve. So let's put, first of all, we're going to put a lot of writing on this. Let's put mu right here. So you know that that's the mean, right? And this spot right here, so this spot right here is all the people who are at this point right here have the mean value, whatever the mean is. Whoa, sorry. All the people who are at this point right here have the mean value plus one standard deviation. So that's 1 sigma, right? The people who are here are at the mean plus 2 standard deviations. So if we look back up here, for example, if the mean for men is 5.8, then those people would be right here at 5.8. These people right here would be at the mean plus 1 standard deviation. So they'd be at 5.8 plus another 0.83, so that'd be at 6.63. These people up here would be 5.8 plus 2 0.83s. So I don't know exactly what that would be in my head, but you know, that's what those people. Up here, you would be at the mean plus 3 standard deviations. Guess what would be down here? It would be the mean minus 1 standard deviation. Here's the mean minus 2 standard deviations, and here's the mean minus 3 standard deviations. That's not a good mu there. Okay? Here's the amazing thing. Mathematicians and statisticians have figured out in a sample, a population, what percentage of members of a population will end up in each of these sections. So in this section right here, between the mean and one more than the mean, 34% of the population will end up there. And remember, it's symmetrical, so 34% winds up there. So what that means, obviously, is between one standard deviation less and one standard deviation more than the mean, 68% of the population falls in there. Okay? The next one up is 13.5% fall between one standard deviation more and two standard deviation more. So of course it's 13.5% down here too. So if we wanted to know how many people fall within two standard deviations of the mean, it'd be the 68 plus another 13.5 and another 13.5, and if you add all those up, you get 95% of people fall within two standard deviations. So that's most people. Okay, we still have a little bit more. Here we have 2.35% and 2.35%. So if we want to know how many people fall within three standard deviations, we would add everything up there and you would get 99.7%. So it's not everyone, but it's pretty darn close. You know, you still have the true outliers. They're really, really tall and they're really, really short or whatever. But almost everybody falls within three standard deviations if it's a normal distributed curve. Okay, let's look at a question or two. Number one, Jim raises Siberian Husky dogs. The weights of adult dogs are normally distributed with a mean of 52.5 pounds and a standard deviation of 2.4 pounds. What percentage of the dogs would you expect to have a weight between 47.7 pounds and 54.9 pounds? Okay, so what you want to do here is you want to kind of sketch what we just did. So the mean was 52.5. That's the mean. And we want to put on here one standard deviation more, two standard deviations more, and three standard deviations more, and one less, two less, and three less. So remember, if this is the mean right here, what this is the mean plus one standard deviation, which is 2.4. So if you add those together, you get 54.9. So this right here is 54.9. To get where the next one is, you add another standard deviation. So that will take you up to 57.3. That's what goes on this one. So we're squishing it in here. And if you add another 2.4, you get what this one is, and that would be 59.7. So that's what goes there. Now to get these ones, you have to subtract from the 52.5. So if you subtract 52.5, take away 2.4, you get 50.1. So that's what goes here. Take away another 2.4 and you get 47.7. So that's here. And take away another 2.4 and you get 45.3. So that goes here. Okay, so I'll kind of draw my normal distributed curve here. And what we're interested in is the number of people who have a weight between 47.7, so that's right there, and 54.9, which is right here. And we have to figure out how many people there are who fit in between these two things here. How many people fit there? Well, remember, we know if this is normally distributed, how many people did we say fit just one standard deviation more? Well, if you don't remember, go back. One standard deviation more, that's 34%. So we would think that 34% of the people would fit in here. How many people in here? The same, it's symmetric, so 34% in here. How many people in there? Well, I'll have to go back and look. What is it between 1 and 2 less? It's 13.5%. So I go back here and I put 13.5%. So if I want to know which percentage of people fall in these areas, then I add up 34 plus 34 plus 13.5, 68, 78, 81, 81.5% of the people that fit in there. Now, if you're really thinking here, you might have a question. You might say, yeah, but these were perfect numbers. What if it didn't say 54.9, it said 55.9? Because 55.9 isn't on here, so how would I know where to put the line? And we're going to talk about that later. We won't talk about that today. For today's work, they'll all work out perfectly like that. Okay? All right. The last question is crazy. It's so much work, so I'm going to never give you a question like this. And I'm going to make this shorter by skipping some steps and stuff. The question asks, does the following data showing the longevity of cell phones in years, so how long cell phones last, does this approximate a normal distribution? Okay, well, there's a couple things you could look for. One thing you could look for is you could look for the mode the mean, and the median, and you could see what they are, and what do you know about how they should be in a normal distributive curve? They should be about the same, and we might as well find the standard deviation as well, okay? So those should all be around the same. So what you would do is you would open up your calculator and start entering in all these values. Crazy, right? You'd hit stat, you want to edit this, and you would start entering in all of these values, 2 and 2.4 and 3.3 and 1.7 and 2.5 and 3.9 and 2.9 and 2.6 and 2.7 and 2.8, and we got them all. And then we would come out of here and hit stat again, and we want to calculate one variable stat, and it was in L1, and now we get all our information we want. So first of all, it tells us that the mean is approximately 2.526. The standard deviation is right here, 0.482. Okay, n is 50. Okay, so there's 50 different data points here. That's good to know. And what else? The minimum is 1.1. The median is 2.55, and the max is 3.7. So the only thing there we can really care about is the median is 2.55. It looks like I wrote this in the wrong spot. That was actually the mean. And the mode, so we have to find the one that's the most common. And why don't you stop the video and hunt for it? Okay, you've looked for it, and I hope you agree with me. I found that it was 2.6. Now, take a look at those first three things here. Is this thing perfectly normally distributed? No, they're not exactly the same. Are those very close to each other? Yes, they are very, very close to each other. So this could be an approximation of a normal distribution. Okay, the next thing you want to do is you want to look at how many of them are one standard deviation more than the mean, how many of them are two standard deviations, etc. So what we should do is we need to break this into sections. So one range of values, which I'm going to write the fourth one up, should be from the mean, which is 2.526, and it should go all the way up to one standard deviation more. So you want to add 0.482 to this, and if you do that, you'll get 3.008. The next one should be from 3.008 to one standard deviation more than that. So add another 0.0482, and you will get 3.49. Add another standard deviation to that, and you will get 3.972. Add another standard deviation, or actually what we can say is anything greater than 3.972. So this is one standard deviation more, two standard deviations more, three standard deviations more, and more than three standard deviations more. Now we have to do less than. So to get that, we want the ones that go up to 2.526, the mean, right? And then you want to subtract the standard deviation to see what the lowest point of that range is, and that would be at 2.044 when I subtract 0.482 from this. That'll be our highest value of this range, and we have to subtract another 0.0482, and if you do that, it'll be down to 1.562. 1.562, subtract another one of these, and you'll get 1.08, and down here is anything less than 1.08. Okay, this is all the ones less than 3 standard deviations, all the ones between 3 and 2 standard deviations below the mean, all the ones between 2 and 1 standard deviations below the mean, and all the ones between 1 and the mean itself. Getting confused yet? Next thing we have to do, believe it or not, is to go through and count how many of these things in here are below 1.08. So that would be all the ones that are basically 1.0 or below, and if I count those, I get 0. I'm going to do this fast. I'm not actually going to do this, but what I would do, and if I'll just do this one right here. Here I'm looking for all the ones between 1.08 and 1.562. I only go to one decimal point here, so that'd be from 1.1 to 1.5. So 1.1 to 1.5 there. And that's it. Okay. Then I'd look from the ones that are from 1.6, I guess, to 2. And if I went through there, I would find 1, 2, 3, 4, 5, 6, 7. That's it. And I'm just going to quickly do the rest. You can go ahead and do that if you want, but you'll get 17 here, 18 here, 6, 1, and 0. If you want to feel more confident, add those up and you should get 50, and I think you do. 8 plus 17 is 25, plus 18 is 43, plus 6 is 49, plus 1 is 50, so that's good. Okay, next thing we're going to do, you could graph this to see if it looks like a normal distribution, but let's just speed things up because this is killer, isn't it? Let's take a look at how many of them are between 1 less and 1 more standard deviation. So this is between 1 standard deviation less and 1 more. Now remember, there's 50 total. So here, 17 plus 18 is 35 out of 50, which as a percent is 70%. So there's 70% between 1 less and 1 more. How many did we say there'd be? We said there should be 68. Well, that's pretty close. 70 is pretty close to 68, so that's looking pretty good. Okay, let's look at how many are between 2 standard deviations. So we have to add all these up. 7, 17, 18, and 6. 35, 42, 48, I believe is what that adds up to. So if we look at that, that's 48 out of 50, which equals 96%. And how much did we say that should equal? It said it should be 95. So again, that's very, very close. And now let's look at how many are between 3 standard deviations. Well, 3 standard deviations is all of them, because these are zeros beyond. It's from here to here. I went too low down here, right? So get rid of that. And if you measure those, it has 50 out of 50 or 100%. And we said it should be what, 99.7? I always forget these numbers, by the way. Yes, 99.7. So is this a perfect normal distribution that we've drawn, this data here? No, it's not a perfect distribution. Is it a good approximation of a normal distributed curve? Yes, very good approximation of a normal curve. Okay, that's a crazy question, isn't it? If I was to give you one, I think maybe I would certainly give you a lot less data than that. Maybe I'd only give you about 20 points instead of 50. That was overkill, and I apologize for it. Okay, hope that makes sense, and we'll continue with this lesson next day.
Let the sky fall.